So today we get to start a new section or new chapter. This time around, I noticed last time there were some that didn't get all of their homework completed, and I think it really had an effect on what you did on your test. So make sure you stay on top of these things and get all of your stuff done, because each of those sections are going to be part of your test. So you want to make sure that you know what you're doing with those. The other thing about chapter 9, it's dealing with radicals, meaning that we're going to have roots and a variety of roots, square roots, cube roots, fourth roots. This is going to follow through with the rest of the chapters for the class. So in chapter 10, we're going to pull some of the stuff back. And in chapter 11, we're also going to pull some of the stuff back from chapter 9. So 9 kind of follows through with everything else that we're going to do for the rest of the class. So make sure that you get down each of the steps as we go through. We're going to go through and break some of these things apart and get them so that they have the actual values of what square roots are, or what the root happens to be. Some of them we're going to do on your calculator, and so we're going to use your calculator today too, so that we can end up figuring out what those come out to be, and giving them, of course, different names that go along with what we have for those. So in starting, we have, of course, roots and radicals, and with these, what we're going to do today is we're going to evaluate square roots. Square roots are the ones that have a simple symbol of a radical symbol, and that happens to be this. And then we also have cube roots, and cube roots have an index involved. So they're going to have something up here that's going to have a 3 in here. So what we're looking for when we look at square roots, we're looking for 2 numbers that give me the value underneath, but we're only going to use one of those. And here we're going to look for 3 identical numbers that give us the value underneath. And when we take the cube root of that, we're only going to pull one of those numbers out. And then we're going to look at your calculator and see how your calculator handles square roots and cube roots, so you have an idea of what to do with those. So first off, we need some definitions of what our values happen to be and what we're looking at. We have the symbol, which is called the radical sign. The number underneath the radical sign is called the radicand. And if I put a 4 under here, I have a square root, and I have a number 4. The 4 is representing the radicand, and that ends up being the thing that we're going to work with. So you get an expression such as the square root of 64 is called a radical, or a radical expression, meaning that we have something that we have to solve in there to come up with it. Now, if you guys probably looked at this, what would be our number? So what would be the square root of 64? Anybody know? So, pardon? 8. Yeah, it's 8, because 8 times 8 gives me 64, and so that would end up being my solution to this one. If I looked at my square root of 4, my answer there would be 2, because if I put 2 back under here and I double it, 2 times 2 is 4, but because of the square root, I'm only pulling out 1 2. Same here, the square root of 84 is 8 times 8, so I'm only pulling out 1 8 to end up with what its square root happens to be with that one. And so square roots, again, they have the square root symbol, and they're a principal root, and the principal root is whatever we're going to come up with for what A would be and what we'd pull out of there. You can have a negative sign out in front of those, and what that simply means is that if we had our 64 in here and I put a negative in front of it, that is simply telling you that when you get finished taking the square root of 64, your answer is really going to be a negative 8, not a positive 8 coming out of here. But do realize, out of 64, it could have been a negative 8 times a negative 8 under here, because a negative 8 times a negative 8 is positive 64. Or it could have been 8 times 8, which would also give me 64. So with square roots, there's a little difference there with what you have happening with those, and what does end up taking place with them. Then, if we look at square roots with negative numbers, if you've got a negative value underneath your square root, we can't do anything with those right now. But what's going to happen is when we get to section 9.7, we're going to end up finding out that in 9.7 we can get to imaginary numbers. And if some of you have probably heard of that before in your previous math lives, the I value. And so that's what this ends up signifying when we get to that point. So then we'll be able to work with those. The thing about negative numbers, if you have a negative number under radical, and under your radical you have a -4, any even root or any even index, so an even index with a negative radicand, there is no solution right now. When we get into 9.7, we'll have a solution for those. But for right now, if you have an even root, such as a square root, a fourth root, a sixth root, an eighth root, and I think you get the idea, if you have an even index out there, you cannot end up taking anything that has a negative value underneath it to come up with what it's going to be. Okay, so do be aware of that we've got some pieces in there and what ends up taking place with those. So what are, before I move on, let me get a blank sheet of paper here. What are the perfect square roots? So if we're going to look at square roots, what are the perfect square roots? Well, if you take a look at 1 squared is 1. The square root of 1 squared will of course be 1. And so if you square 2, you get 4, but the square root of 4 is going to end up equaling 2 when I take the square root of it. So these are considered to be perfect squares. So basically what it's doing is taking your base number, squaring it, and ending up with what your value is going to be. So if I take 4 and square it, we'll just list all of them in here that you're probably going to run across. Gives me 16. The square root of 16 is 4. 5 squared is 25. So that's going to be the square root of 25, or 5. 6 squared is 36. Square root of 36 is going to equal 6. And 7 squared is 49. These again are all of the middle pieces of your multiplication table. And then also 9 squared is 81. Square root of 81 is 9. And if we did 10 squared, square root of 100 is equal to 10. 11 squared is 121. And that's going to equal 11. And we, of course, could keep going on and on and on with these. So if you have a perfect square on your calculator, you can end up finding out whether it's a perfect square. So if you had 169, is that 169 and take the square root of it, is that a perfect square? So if we look at it and think, I don't know. So on your calculator, if you bring your calculator into this, what you will have is on your calculator, is that showing up? Oh, maybe this camera up here we got now is better than the last one. That's good. So if I want to do a square root of 169, I would go, my square root is right above my x squared on my calculator. So here's my x squared. So I would go second x squared. It's going to give me a square root piece in there and put 169. And then if I hit enter, it's going to give me what that square root happens to be. And in this case, it's 13. So 13 times 13 is a perfect square. But if you had something like the square root of 124, and you go second square root and put 124 in and hit enter, it comes out as a decimal answer. So I know it's not a perfect square. So 124 is not a perfect square because I get a decimal representation in there. So keep that in mind because you're going to run across those that are not perfect squares. And in 9.2, we're going to work with those and figure out what we can do to make them be a perfect value. Because as soon as you go to a decimal and you round it off, it's not perfect anymore. It's not exact anymore because we've rounded it off, and so we've made a change in it. But we'll get there as we go through these. So again, keep in mind, these are all of your perfect squares that you're probably going to run across. They don't have a tendency to get into too much more than those. Square roots, evaluating them. And it says 64 has 2 square roots, one positive and one negative. We talked about that. Under the radical sign is understood to represent a positive square root or the principal square root. And a negative represents the negative square root. So if you have no negative out in front, we're going to look at it as being a positive 8. If there's a negative out in front, we're going to look at our root as being a negative 8. So just pay attention to that with your negative signs in there. And then they give you another example down here. 11 squared is 121. The square root of 121 is 11. And then also the square root of a negative 121 is a negative 11. So keep in mind when those signs end up showing up in there. This one, square of 0 is 0. The square root of 0 is 0. So we know that that's 0, but does that have really a lot of meaning to us? Not really. It's kind of like the square root of 1. Square root of 1 is 1. So the square root of 0 is just going to end up being 0. Now this one, because it's a negative underneath my radical, I cannot do that. It has a non-real number. So we would basically say in this case that I can't do that one right now. We're going to do it later on, and that's going to come up in 9.7 when we have imaginary numbers that we can work with. And then imaginary numbers pop up in chapters 10 and chapter 11. Not so much in 10, but more in 11 with that one. So do be aware of those. Cube roots. Cube roots have an index of 3. So if you run across a root that has no number up here, it's a square root. So cube roots have that 3 in there. So what are some cube roots? So if I take 1 and cube it, we're going to go through and do the same kind of thing we did with the squares. 1 cubed is 1. And if I want the cube root of 1, it's going to be regular 1. If I have 2 cubed, that's 8. Cube root of 8 is 2. So I go automatically right back to my base. And notice my base was raised to the 3rd power. Because this is a 3, I could have also looked at this as the cube root of 2 cubed. When these two match, that means I can pull out that base. And we're going to do a lot more of those in 9.2. So 3 cubed is 27. So the cube root of 27 is, of course, 3. 4 cubed is 64. Cube root of 64 is 4. 5 cubed is 125. So the cube root of 125 is, of course, 5. 6 cubed, so 6 times 6 is 36. Times 6 will give me 216. So the cube root of 216 is equal to 6. And that's kind of the highest that if you know those, that's going to be the things that are going to help you out. If you don't, yes? To do cubes? Yeah, I'm heading there right now. Yeah, the question was, can we do them on our calculator? Of course. With your calculator. Yeah, well, on your calculator, your cube root is not on the face of your calculator. Your cube root is under your math button. So if you hit math, you'll find that your cube root is down here under number 4. Also, your cube is here, but your cube is not as important to use in there because you've got your caret key to use otherwise. And so if I want to know a cube root, so if I said, Cal, I can't remember what the cube root is of something, I can end up going here and putting that in. So when you do that, we're going to go down to number 4. So you can either arrow down to 4 or simply type a 4. And it's going to put your cube root in there, okay? So if I want to know the cube root of 729, for instance, and I don't know if it's a perfect cube or not, and then I can just hit enter, and it comes out to be 9, so I know that's a perfect cube, all right? so we can get perfect cubes in there. So that's the way to do those. Now, if it's not perfect, and you go to math, you go down to 4, and you have 138, and you want the cube root of 138, we then hit enter, and that's my cube root of 138. And I know it's not exact because of the decimals that are in there, okay? And it will tell you in Hawk square to round. So it'll say round to the thousandths. So if I said to round this one to the thousandths, I would be 1, 2, 3, where the 7 is at the thousandths, the 6 will make the 7 become an 8. So then my rounded answer would be 5 and 168 thousandths would be the correct answer for that. So you want to watch those and make sure that you got, if they're perfect, they will come out like the 9 did up here. If they're not perfect, you'll come up with a decimal representation for those. Okay, so that's how we work with our calculator. Questions with calculator? And you think you're okay? So again, it's under math, number 4. And you can find it right there. Now, some of the older calculators of the TI-83s, you need to close it inside of a parenthesis because they put a parenthesis in there. So if your calculator does that, you'll see a parenthesis pop up, and then you just close it with a parenthesis at the tail end. This one's an 84, and so it doesn't show the parenthesis in there, but there is. So you would have that in that value. Okay, so that's how we work with our calculator with this. So we've got cube roots. Now, the thing about cube roots is that if we look at those, in a cube root, the expression is 3, the cube root of a. The number 3 is called the index, which we talked about that. In the square root expression, such as the square root of a, the index was understood to be 2, and it's not written. So be aware of that some of these don't show. Expressions with square roots and cube roots, as well as other roots, are called radical expressions, and we kind of went over that so that we know that is what they are called. And so we can end up getting that part in there with those. So the other thing about cube roots, and I guess I should stick that on here, is that if you have an odd index, the radicand can be negative. Okay, so it can be negative. The reason being is if I had the cube root of a negative 8, the cube root of a negative 8, under here, I would have a negative 2 times a negative 2 times a negative 2, because a negative 2 times a negative 2 is positive 4, times a negative 2 is a negative 8. So therefore, when I pull that out, there is no question of whether the answer is a negative value or whether it's a positive value, because if any odd exponent out here, or odd index, I should say, I can come up with that value if my answer underneath is negative. So odd indexes would be things like the cube root, the 5th root, the 7th root. So all of these, I can end up coming in having a negative radicand underneath. But anything even, I can't. So do keep that in mind that you can't have it underneath the other ones in there. So that's kind of the piece that's in there. So if we look at cube roots and we look at what happens with those, 2 cubed is 8. Cube root of 8 is 2. Cube root of a negative 6 is a negative 216. Or the cube of a negative 6 is a negative 216. The cube root of a negative 216 is a negative 6. And again, note that cube can be negative as long as the index is odd under there. If you look at fractions, we have 1/3 cubed comes out to be 1/27. The cube root of 1/27 goes back to 1/3. And we'll talk more about fractional pieces and what we do need to do with those when we break them apart. And so that's that piece. Okay. So we've got that out of the way. Evaluating radical expressions with your calculator. Some of these in your Hawks examples, they're going to put a number in front of it. This is an order of operations problem. So if it's an order of operations, again, please excuse my dear Aunt Sally, or parentheses first, followed by exponents. But in that level of exponents, we're going to add roots. We haven't added roots before, but roots are on the same level as exponents. So that's your second step. So you would end up getting the square root of 3. But do we know what the square root of 3 is? When I was in college, I'm going to date myself here. When I was in college, we didn't have calculators like you guys have today, graphing calculators. They came out, what was it? Probably after I completed my math portion of my degree. But they came out later. So we had to estimate these. So the square root of 3 fits somewhere between the square root of 1 and the square root of 4, so we would have to estimate what that would be. So you guys got a whole lot easier, because all you need to do is plug it into your calculator to go through and get it. But you got really good at finding them because you started to see what your comparisons happened to be. But again, we had to do that. Or we had charts. Books had big, thick charts in the back. You can go back to the chart where they'd worked them all out, and then you'd locate it in your chart. For us, though, because we do have our graphing calculators to help us out with these, simply all we need to do is plug this one into our calculator and let our order of operations within our calculator take over. Now, it will follow what you put in. So be really careful when you enter that stuff into your calculator, because order of operations is built in here. If you put something in an opposite order of what you see it here, it may not solve it correctly. So be really careful. So put 1 plus 2. Now, because these two are back to back, what does that mean? Means to do what with them? Multiply. Perfect. Yeah, so I put multiply. Then I want my square root, so I got to go second square root. Put in my 3. Now, on the older calculators, you would put a parenthesis here if you did your square roots, and so that it knows that you're done. Then hit enter, and you will get your answer. And so that basically follows along with those stuff in here. Entered 1, plus key 2, press second. They didn't put their multiplication in here, and some calculators just handle that and other ones don't. So to be safe, I put my multiplication in there so that I knew that I was getting it multiplied. Then it goes through, hit enter, and you end up getting the answer that we have here. And so it worked out correctly. And it will tell you to round to a certain spot. So in this case, if we're going to round to the thousandths, we'd find the thousandths, which is 4. Look one place behind it. The 1 is not going to change to 4. So my answer that would be typed in would be 4.64. And so that's what I would put in for my answer, not the whole thing. Okay, so you want to make sure that you are really careful with that and get your pieces in there. Another thing that's not in here is they give you some combinations of looking at different things and seeing what you have. If you have a perfect square root, such as 4 under here, if I got the square root of 4, that ends up giving me a 2. This is considered to be a real number, okay? So it's a real number, meaning that it has no decimal portion to it. If they gave you the square root of 5, and you put the square root of 5 on your calculator, which I can't end up doing without it, so second square root 5, and I get, this is a decimal answer, I get 2.236067977. That is considered to be an irrational number. Irrational because it goes on indefinitely and never ends. So it's irrational because, again, of the decimal portion. If they gave you the square root of a negative 4, this is what's considered a non-real number. So be aware of those. There are questions that will pop up in Hawks, and it will ask you to pick whether it's a real number, an irrational number, or a non-real number. So do be aware of those, and they do show up in there. So if they were to give you the square root of 4.84, and ask you to solve it. And if I put that on my calculator, so I go second function, square root, and put 4.84 on my calculator, and I end up with an answer of 2.2. This is also considered to be a real number. So be careful if it comes out as a terminating decimal. This one's a non-repeating, non-terminal. This one's a terminating. So terminating decimals are considered to be real numbers if that happens and pops out for an answer that you have. Okay. Questions on any of that so far? Or we're so far so good. Okay. Now these in your first section are going to be ones that will come out to be actual answers for these. So let's take a look at these practice problems. We'll go through them because there wasn't really many problems that were falling into place in here. So what's the square root of 49? 7. What's the square root or the cube root of 125? Now if you can't remember what it was, put it on your calculator and come up with, what would it be? 5, yep. Cube root, or the square root of a negative square root of 25. And square root of 196. And again, you can stick it on your calculator and pop it right up, and it will be 13. Then, number 5 down here is a fraction. But within this fraction, 9 is a perfect square, which is 3. 16 is a perfect square, and so you get 3 over 4. How about the square root of 324? Okay. Square root of a negative 25. Shaking your heads out there. No, I can't do that one. That's a non-real for us right now. Later on, it won't be. What about the square root of 3? What will it end up being? So square root of 3. Put that on your calculator. 1 point, what was it? 32? Did you round it? No? Yes? Okay. All right. So it's rounded. So that's what our values would be. But then let's go back and identify and determine whether each number is rational. Rational are those real numbers. Irrational or non-real. So number 5, what would we classify it as? So it's an exact answer, so it's rational. Square root of 324 is also exact, so it's rational. We already identified this one as non-real because we can't do it. And then finally the last one, because it's a decimal and we rounded the whole thing off, it's irrational. So we got irrational with that one. Okay, so that ends up being the pieces there. And then these two are ones that you can put on your calculator. So let's see what we get for an answer to those. So this one, we are going to go through and let me hit clear on that one. And so you're going to go 5 times second square root 2, enter, and we get that, and it says round to accuracy of 4 decimal places. So 1, 2, 3, 4. So the 6 is going to make the 0 become a 1. So my answer is 7.0711 for that one. And then finally the last one. What would we end up putting in for this one? The calculator show up in there. So what would it come out to be? And that one ends up being a negative and round to 4. 1, 2, 3, 4. A 0 after it, so it stays a 0. Negative 4.580 or 830. So that would be my solution to this one. Okay or not okay? What do you think? Okay, and that's all there is in that section. So it's a pretty quick section, goes by pretty fast. It's just kind of getting you used to what you end up doing with your problems in there. And so that's that one. This is just happens to be the answers that went along with what we just did. So that's that piece. Again, it's just getting you used to the idea that you can use your calculator and you got some perfect cubes and perfect squares and those kinds of things. Now what we're going to get into in 9.2 is simplifying these things, but they're not perfect anythings. They're not perfect squares. They're not perfect cubes. And so we have to have ways, but we want to have them be a non-decimal answer. And so we're going to work with those. And so simplifying radicals, including square roots and cube roots. And so we're going to take a look at those. There's two ways of looking at these, and these are kind of square root properties. So if A and B are positive, because we want to keep them positive because we got square roots of real numbers, then A times B will equal the square root of A and the square root of B, meaning that if I have two things that multiply to give me a value, I can break those two things apart. So an example might be 64. 64 could be broken into 8 times 8, okay? Because I could break it apart and come up with two factors for it. Is that going to help me? No, because 64 happens to be a perfect square, so I would not want to break it apart like that because I know my answer to 64 is just plain 8. But if I had the square root of 50, I might want to break apart like that because 50 is made up of 25 times 2. And so what I'm looking for in here, and this is just one method of doing that, is to look for perfect squares that are factors of that number. Okay, so the 4 or the 2, the 4, the 9, the 16, the 25, the 36, the 49, and the 64 and 81 are things that I would look for in here. Sometimes that's a tough way to do these, and I'll show you a different way of looking at those as well. But what my answer would come out to be is the square root of 25 is 5 times the square root of 2, and that is pretty much exact. If I put the square root of 50 on my calculator, I'll get a decimal. And so we didn't want decimals at this point with these. Then in a fractional piece, we can break apart each piece. So we could say the square root of the numerator and the square root of the denominator. Later on, we're going to force these denominators to be perfect, but that's again not today, but down the road we will. So an example, if we went back to that 9/16 that we had earlier, that would be the same as the square root of 9 over the square root of 16. And so therefore, if I break that apart, I'm going to end up with the square root of 9 is 3, square root of 16 is 4. So my answer comes out to be 3/4. So these are things that are going to help us break these things apart so that we can do a little bit of different stuff with them to come up with what our values happen to be within those. And the simplest form for a square root is considered to be in the simplest form when the radicand has no perfect squares as a factor, meaning that I cannot remove anything else out of it. And I have broken it down to as far as it's going to be. So every one of these answers in 9.2 is going to have a radical. The radical's not going away. In 9.1, they all went away. So here, we're going to leave them in place. So let's take a look at some of these and see if we can break them apart. So let's first take a look at the square root of 48. Now, if you look at 48, you might look at it and say, oh gosh, I don't know, what combinations make 48? So it's hard sometimes to say, okay, I'm going to look and see, does my perfect squares go into this? Well, 4 would go into it, wouldn't it? 4 would go into 48, we all agree? Goes in there 12 times. Then 4 would go into 12 again. So we would have two groups of 4s. We could look at 9. 9 doesn't go into there. 16, does 16 go into 48? What do you guys think? 16 into 48. it'll go in there 3 times. So one method is to break it down to 16 times the square root of 3. Square root of 16 times the square root of 3. Square root of 16 is a perfect square, so that's a 4. And the square root of 3. This is one way. Now I know it makes it looks like, how am I ever going to find what these perfect squares happen to be within this? And second method, and this is a method I tend to like more than this one. This one's kind of like a method 1. Method 2 is take 48 and break it to its prime factorizations. Now you might say, oh, God, that's going to take me a while. But really it doesn't. So 2 will go into 48. 20, or well, actually, why don't we use 6 and 8? Because 6 times 8 is 48, because it doesn't matter what we put here. 6 is 2 times 3. 8 is 2 times 4. And 4 is 2 times 2. So what I end up getting out of this when I break it to its prime factorizations is I start to see combinations. 2, 3, 2, 2, 2. Really, 48 is the square root of 1, 2, 3, 4 2s times 3. Since my index out front here, my index is 2, what I can do now, if I break it to its prime factorization, is I can look and say, how many times does 2 go into these indexes on here? 2 goes into 4, how many times? So my index goes into that exponent 2 times. So that means I can take a 2 squared out. 2 goes into 4 evenly, so there's no 2's left. Does 2 divide into the exponent on 3? Not at all, right? So 2 does not go into 1, so the 3 has to stay underneath my radical. 2 squared is 4, the square root of 3. I did not have to start thinking about where do I have any perfect squares in there and what perfect squares are going to go into that. Like over here, I had to figure out, okay, what can I break out of there? I didn't have to do that in this case. All I did was to break it down to its prime factorization, looked at my index and said, how many times does it go in there? Pulled that number out. So 2 went into 4 twice, pulled out the base of 2, squared, left the 3 underneath the radical, squared my 2, and ended up with 4, the square root of 3. So I don't know. What do you think? I need to do another one like it. We'll see what happens. 63. If you look at method 1, what is a perfect square that's in 63? 9. So 63 could be broken down to the square root of 9. 9 goes into 63, 7. Square root of 9 is 3. So I'm left with 3, the square root of 7. So if you can figure out those, you're good. If you can't, do the prime factorization. So 9 times 7. 9 breaks down to 3 times 3. And 7 is 7. So under my radical, I have 3 squared times 7. Index again outside here is 2. So 2 goes into the exponent once, so it pulls out a 3, leaves the square root of 7. So I'm left with my value in there. And I didn't have to think in this case of any perfect squares. All I had to do was get my prime factorization so I could see what was in there and what would break it apart with that one. So if I go to my fraction, what would happen with it? So if I get the square root of 75 over the square root of 16, 16's easy because that's 4. So the square root of 16 is 4. What about 75? What makes 75 up? If we're looking at perfect squares again, what would be my perfect square that goes in 75? So it'd be 25 times 3, or my answer would be 5, the square root of 3, all over 4. Okay? If you didn't like that method, 16 is a perfect square, so I knew that one. And take 75, and it's 3 times 25. 25 is 5 times 5. So I end up having 3 times 5 squared. Again, my index is 2, so doesn't go into 3, but 2 will go into 2 on the 5 once, and that makes me pull out a 5. So my answer is 5 to the square root of 3 all over 16, which was 4. So I don't know. Thoughts? Guys, okay? Yes. Nope, because you got to put the 5 back underneath. So if I was going to put it back underneath, I'd have to square it to put it back underneath to get 75. Okay? But if I take on my calculator, grab my calculator, and if on my calculator I put the square root of 75, and it equals 8.66025, okay? Now, if I take what I found here and I put it on my calculator, 5 times the square root of 3, and hit enter, just like we did in the previous section, I will get the exact same answer. Notice how they're the same? Okay. It's just that this is exact. This would have to be rounded. Okay. This is perfectly exact as you can possibly get it. Yep. With that one. And so you want to make sure that you get your perfect stuff in there and come up with those. Okay. Questions with this at all? Good question to ask, though. It does make it look weird. It makes it look like it can't be the same. They can't equal each other. But in the long run, they do equal each other. Okay? Because you're pulling out the perfect square pieces out of that radical and coming up with those. Okay. So let's take a look at some more in here and see what we can do with these guys. When they don't only just leave it with numbers, they start putting variables underneath as well. And the variable pieces, when they do that, is you pay attention to your index of 2, because these are all squares, but you pay attention to your square root, and it's a 2, and you only take in to figure out what comes out with a variable is the 2 divides into the 2. And figure out how many groups of those you have and how many extras you have left over. And so you can pull those out. So if we look at this very first one, the square root of 16, what is the square root of 16? So we can break it apart to the square root of 16 times the square root of y squared. So 16 is 4. Y squared, there's again a 2 sitting right here. So 2 goes into 2 once, meaning that that is my new exponent when I pull my y out. So my y is going to be to the first power. So my answer is 4y to the first power. So you're looking at combinations of what type of stuff you can haul out of there and move out of there. So what about this next piece, 72? If you continue with method 1, you're looking for a perfect square in 72. So what perfect square will go into 72? Can you see it? Kind of hard in this case, because 72, you might look and say, oh, 9. And 9 times 8 is 72. But within 8, there's another perfect square of 4. So as they start to get more complicated, that's when that second method really helps you out. Because if I take 72 down here and break it to its prime factorizations of 9 times 8, 9 breaks down to 3 times 3, 8 breaks down to 2 times 4, and 4 breaks down to 2 times 2. We all good there? With what I did to break my prime factorizations apart? Again, it's saying I've got what factors gave me 72, what parts break that apart, what parts break this apart, and come up with my answer. So under my radical, I have 2 times 2 times 2. I have 3 times 3, or 3 squared, and I have an a squared. So now if I look at my index out here, which is 2, 2 goes into 3 how many times? Once with 1 left over. We all agree? So if it goes in there once, that means I can pull out a 2 to the first power, but under my radical, it's going to leave whatever's left over. So it leaves a 2 under here. So 2 went into 3. So if I take 3, divide it by 2, I get 1 and I have a remainder of 1. The remainder means I leave that base underneath that radical to that power. Whatever that 1 is, whatever that remainder is, that's the power that's on it. Then if I look at 3, 2 goes into 2 once, means I can pull out a 3. No remainder, so that doesn't stay under there at all. We good with that part? 2 goes into 2 on the A, that means I pull out 1A, and so this becomes my answer. But now I need to multiply 2 times 3, and I get 6A, the square root of 2. This becomes my simplified answer, okay? So that becomes a simplified piece to this one. So if you break your pieces apart, then you can end up seeing what comes out of it, and what pieces stay under it, and what pieces remove, and what comes out of it. So I think it's a little easier. I would have had to look at 72 to get a perfect square out of it of 36. 36 times 2, it's hard to see that. But if I get my prime factorizations of these and I break it down that way, I can start seeing what's in there. So if I do the same thing over here to 12, 12 is 3 times 4, 4 is 2 times 2. So once I do that under my radical, I have 2 squared times 3, x squared, y squared. Index is 2. So I look and see how many times does 2 go into the exponent parts in here. This 3 is to the first power. 2 goes into 2 once, so I can pull out a 2. 2 does not go into 1. So if it doesn't go into it, that piece stays under your radical. Don't pull it out. 2 goes into 2 on the x once, I can pull out an x. 2 goes into 2 on the y once, I can pull out a y. And so that ends up being my piece that I have on that, okay? So 2xy, the square root of 3. And that is my exact answer, okay, for this one. Okay or not okay? What are you thinking? Not hearing anything out of you, so I'm hoping you're good. I'm hoping we're getting where we need to be with those. Okay, let's see what happens with these guys. See if we can make some headway out of them. This one, 81. If you follow the system that I've been showing you, breaking it apart, do we need to break it apart? No, because 81 is just plain old 9, right? Because if I can recognize perfect squares, I don't have to go through and do all that other stuff. But if they're not perfect squares, that's when I need to break it apart. And the index, again, is 2, because it's a square root. 2 goes into 4 twice. That means I can pull out an x squared. Is there anybody left? Nope. That's the final answer to that one. Okay. This next one, index again is 2. But what do I know about 64? Is 64 a perfect square? It is. So I can pull out an 8. 2 goes into 5. So 5 divided by 2. The number of how many times it goes in there, that is your exponent on the base. The remainder is the exponent on what's left under the radical. So 2 went into 5 twice. So that means I can pull out an x squared. But it's going to end up leaving inside of here an x to the first power, or just a plain old x, okay? So I can pull out a square, but I leave an x. What about y? Y is to the first power here, so 2 doesn't go into the first power, so y stays under my radical. So my answer to this one is 8x squared, the square root of xy, okay? In your keypad in Hawks, it will have a square root. It has a root. I think you don't have to put the index in, just put your value underneath. It's because it'll have a spot for an index in there. So you can just pull that part out and come up with what your answer is. So what do you guys get on this one? We'll let you work on that one for a little bit and see what comes out of that problem and see if we can get an answer to it. So if you can identify that 9 was a perfect square, you could have just pulled out your 3 and not broke it down. But if you didn't know that 9 was in there and you broke it apart, you could get your exponent values of everything and then pull out what you can. 2 doesn't have a high enough one to pull out, so I leave it. 3 is squared, so I pull out a 3. A to the 4th, 2 goes into 4 twice. So, and there's nothing left over, so I get a squared. 2 goes into 6, 3. Pull out a b to the 3rd power, and that becomes my answer. So as you do that, you pull out these different pieces in there to come up with what your answers would be. Okay. Last one is yeah, because then we're going to go to cubes. So what comes out of this thing? What would end up being my values that I would work with? Well, if you look at your squares, 9 is a perfect square, so I can pull out a 3. The index out here is again 2. So how many times does 2 go into 13? 6 times, right? So I can pull out a to the 6th, but there's a remainder of an a, because 13 divided by 2 is 6. This remainder is what the exponent is on that a, so a has to stay underneath the radical and also come out. What about b to the 4th? 2 goes into 4 twice, and so I end up with a b squared that pulls out in the bottom. So that becomes my value, okay? So in working with these, index of 2, remember it's always every time you reach a group of 2, you can pull those things out from underneath there. So every time I see 2 things, I can yank those out. If you want, you could expand that a to the 13th and write a times a times a times a 13 times and circle groups of 2s. You're still going to get 6 groups of 2s with a single a left over. So that's another way of looking at that too. In cubes, they're same way, but we're going to simplify them. But now instead of looking for 3 items to pull out, I'm going to look, or 2 items to pull out, I'm going to look for 3. So a cube root is considered a simplest form when the radical has no perfect cubes as factors. So we're going to see what we can end up doing with cubes. So same process. The process isn't any different than what we just did, but now instead of having an index of 2, we're going to look for 3. So we're going to look for 3 items that we can pull out. So what is a perfect cube in 54? Perfect cubes, again, are things like 8, 27, 64, 125, so you get bigger numbers to look at. That's where breaking them apart into prime factorizations sometimes can really help you out with these. So 2 goes into 54 27 times. 27 is 9 times 3. 9 is 3 times 3. So if I do my prime factorization of 54, then what I got left under here is 2 times 3 cubed, x to the 6th. So now instead of looking for 2 things to pull out, every time I get a 2, I'm going to take everything out once I get a 3. So 2 has to stay underneath the cube root. 3 goes into 3 once on the 3, so I can pull out a 3. 3 goes into 6 twice, so I can pull out an x squared. So it's not really any difference. The process is still the same that we end up doing. Now we can have negatives, like we've got a negative 40. So if I take 40 and break it apart, I end up with 2 times 20. I end up with 2 times 10. I end up with 2 times 5. And if you've got a negative, just simply put a negative 1, which means I'm going to pull out a negative 1 whenever I do that. Okay, so if you've got a negative, it means your answer is going to be negative when you take the cube root of it. And I've got 1, 2, 3 2s times 5. And x to the 4th and y to the 13th. So I cannot pull out, I can pull out a 2. I cannot pull out a 5 because there's not enough of them. 3 goes into 4 once. I can pull out an x, but it leaves a remainder of 1, so I have x under my radical. 3 goes into 13 4 times, leaves 1 left over, so I pull out a y to the 4th power, and I leave a y under my radical. So my final answer to this one is a negative 2x y to the 4th, the cube root of 5xy. Okay, that makes sense? What do you guys think? Yes? No? Hopefully. What happens with the last one? See what you can do with it. Use that prime factorization to help you out with these, because it's a whole lot easier to see what you're pulling out then, instead of looking at it without that and coming up with those. It just gives you a great place to start with it. So use that to your advantage. Yes. Yep. A to the 8th, B to the 11th. And you can't really stick these on your calculator because you want an exact answer. You could get the cube root of 250, but it won't be exact. So we're trying to find exact things. So keep that in mind, that you can't just put it on your calculator and kick out a decimal answer. It doesn't work that way. So we got to come up with what the true values happen to be with these. With this one, you got quite a bit left underneath your radical, because there's a bit of stuff that doesn't come out when you're working with that one. So be aware of that, that there'll be pieces left under there that don't come out. Okay, so when you break it apart, 250 becomes 2 times 5 to the 3rd power. 2 has to stay under the radical. 5 to the 3rd power, I can pull out a 5 because 3 goes into 3 once, so I pull out a 5. 3 goes into 8 twice, leaves me 6 from 8 is 2, so I pull out an a squared, but I leave an a squared under my radical. Then 3 goes into 11 3 times, so b to the 3rd comes out, but my leftover is a 2, so it stays underneath my radical. Okay, so I can see what pieces need to be left under there with that one. Okay, what do you think? And then there's some extras in here that are examples of some practice problems. So let's go through these and see if we can break them apart and come up with what our values would end up being for those. 192. So if we break 192 apart, That one breaks apart. It's got lots of pieces to it. So I have 1, 2, 3, 4, 5, 6 twos. And I have 1 single 3. So I can pull out a 2 to the 3rd power, leaving under the radical a 3, or I can pull out 8 and have the square root of 3 that's left under there. 32, if we can look at it, 16 is 16 times 2 makes 32. So if you can look and know what your perfect square is, you can still do it that way. So we're going to pull out a 4, and we're going to pull out an x, and we're going to leave a 2 underneath the radical. This one breaks into 2 pieces. Square root of 3 stays, but the square root of 4 becomes 2. Then we're into square roots here. 54 is 9 times 6. 25 is 5 squared times x squared. So in this case, I can pull out a 3 and a y squared. Under my radical leaves a 6 and a y. And in the bottom, I have 5x. This one, what happens to 120? See what you get. What can come out of 120? But we've got a cube root. So this time I need to do a cube root of that one. So I'm looking for 3 things I can pull out. And again, if you can use that prime factorization, sometimes it helps you. So 120 is 2 cubed times 3 times 5. So I can pull out a 2, and underneath my cube root leaves 3 times 5, or 15. And then finally the last one, 32. 5 twos. 3 goes into 5 once, pulls out a 2, leaves a 2 squared. 5, 3 goes into 5 once, leaves an x squared. Or I have 2x, the cube root of 2 squared is 4x squared. So what do you guys think? We good or not good? Again, it's like little mysteries are inside of each of these, and if you break them to their prime factorizations, you're good at what you got, and that was the answers to those. Are we good, or you think you need some more? Think we're fine? Okay. All right. Again, these methods that we're learning right now, we again use them throughout Chapter 9. They don't go away. It's not like you learn it at one section and not use it for the next. So we're going to keep doing that. Also, you have that extra credit stuff, Chapter 5, 1 and 5.2, A and B. Those tie into next time because we're going to work with indexes that are fractional, because we're going to take all of these things and turn them into fractional values. So knowing those laws of exponents are going to help you out with the next bunch of assignments. So make sure you do those extra credit pieces. Right?